This is a tree map for Chapter 5 of AP Computer Science Principles. Chapter 5 covers 3 of the big ideas in AP Computer Science Principles. One of the big ideas that Chapter 5 deals with is abstraction. There are a couple of different abstract ideas that are in Chapter 5. One of them was in Logo 2, you started using parameters. Parameters are inputs for procedures. Parameters allow your procedures to become even more abstract, and I'll give you an example of how. When we did Logo 1, we did a procedure called square 20. And that procedure made a square with side length 20. And then we made a different procedure called square 40, and that procedure made a square with side length 40. In Logo 2, we made one procedure called square, and we used a parameter called length, so that if you ever called square, you would input how long you wanted your side length to be, but you didn't have to have a whole separate procedure for the different size of squares. So that local variable is called a parameter. It's an input for a procedure. It's a local variable because you only use it within that procedure, as opposed to a global variable which you can use throughout your whole program. There was also some talk in the bookwork about functions, so please take a look at what a function is. A function is also a procedure, but it's a procedure that has an output. So you might have a procedure that's called the square root function or the root function, and maybe you'd have your number equal to, and you call your procedure that's called square root, and maybe that has an input of 9 and an output of 3, and then your num variable would have a 3 in it. So a parameter would be an input that you can put into a procedure, and a function is a type of procedure that gives you an output when you run it. We also had a data abstraction in this chapter. The data abstraction that we used was a list, and for a list, we even talked about parallel lists, where you had a list of questions and a list of answers, and if you were at the same index, which is the number of the item in the list, if you're at the same index, then you're talking about the same question. So index 3 is hidden figures, and if you're at index 3 on the pictures, you have a picture of the women who were computers that inspired that movie, and if you were at index 3, the answer in the answer list, that would be the answer hidden figures. So the power of a list as an abstraction is now you don't have to worry about what the questions are. You just know that you have a list of questions. You don't even have to worry about how many questions there are, because you can have a length of list and figure out how long it is when you get to it. So that abstraction lets you not worry about those details, but just worry about writing a quiz app for any set of questions that you want. Okay. The other big idea, and this one actually is a huge deal in Chapter 5, is algorithms. First thing we did with algorithms was we talked about the search algorithms. And there are 2 big search algorithms that we talked about. We talked about binary search. Binary search is if you have a sorted list and you're trying to find an item, it's the most efficient way to do so. We said that it takes log base 2 of n guesses to find the key or not find the key, depending on whether it's there. So if you had 32 items, it would take you 5 guesses to find the key if you're using a binary search. For a binary search, you first guess the middle item, and then you guess the middle of what remains until you finally narrow it down to the actual item. Binary search, of course, is preferred if your items are sorted. If they're not sorted, then you have to resort to linear or sequential search. Linear or sequential search just means you're going to guess every single item in order until you are lucky and hit on it. Worst case scenario, it's going to take you n guesses because it might be the very last item in the list, or it might not even be in the list. So those were the two search methods that we talked about, and then we also talked about sort algorithms. Sort and search, you should have those ideas kind of separated in your mind as different things. Sort is taking a list and putting it in order. We said that one of our sort algorithms is the bubble sort. For the bubble sort, you are always going to have the biggest number bubble off to the side, or to the right. It's going to take n squared comparisons to sort a list using bubble, worst case scenario. So as we're analyzing the efficiency of bubble, we say, oh, it's about a quadratic, it's about an n squared. And remember, that was even an estimation. We didn't get a number as bad as n squared, but we just estimated it that way. And then we had merge sort. For merge sort, you divide your data into sets of 2, and you sort the set of 2, and then you put it into sets of 4, and you sort the sets of 4. And we said that we're going to approximate the merge sort as n times log base 2 of n comparisons. And again, that was an abstraction. That wasn't the exact number of comparisons, but it was good enough. And the merge sort, we said, is going to be a little more efficient than bubble. And then we said, well, there's a third sort method, which is called bucket. And for bucket sort, we just set aside all the numbers that we think we might use, and then we look at our number and put it in the correct bucket. Since our buckets are in order, we never actually have to do comparisons. It's not a comparison sort. But we said that we do 2n movements. We take an item and we look at it, we put it in a bucket, and then at the end we take all of our items out of the bucket. So each item gets moved twice, once in the bucket and once out of the bucket. And we also said that bucket sort, even though it's faster, takes more memory. And the reason it takes more memory is because we're reserving that space for each of our buckets. And we don't know if we're going to need them, but we put the space aside before we start the sort so that we can put our items in buckets. Those ideas also, as we were thinking about efficiency, we also said, well, there are some limits of algorithms. And there are some problems that can't be solved with an algorithm, and those are called undecidable problems. So those ones, you just can't write code that would solve those problems. So not every single problem could be solved with a computer. And then there are some intractable problems. And an intractable problem is one that you could certainly program a computer to solve it, but it would take so long for the computer program to run that it's just not worth it. Intractable problems can actually protect us. They protect us when we make up passwords, because it turns out that if you're going to brute force guess somebody's password, it's going to take an exponential number of guesses to come up with all of the total password combinations if people make a long enough password. And we said that these intractable problems protect us, but sometimes we want to solve at least approximately an intractable problem, and we said that the traveling salesman problem was an example of an intractable problem, that we can think of a reason why we want to solve that, especially if we were trying to figure out how the UPS truck should take its route. And so we said, well, there's a heuristic algorithm which we can use, the nearest neighbor algorithm. And the heuristic approximation helps us attack an intractable problem. It's an approximation, so it's not the exact answer, but sometimes it can be a good enough approximation. And then the third big idea that we looked at in Chapter 5 was programming. There were two big programs in Chapter 5. There was Logo Part 2. And in Logo Part 2, you learned how to program with parameters. And you were introduced to the idea of a function. And then there was a quiz app, which you spent some time at. And the quiz app had a lot with parallel lists. And you were programming with parallel lists. You learned how to select an item from list. You also learned a new kind of control structure, a new loop, which would be a for each item in list loop. And if you did the homework, the book questions, you also learned about append. And for append, you need the name of a list, and you need what item you'd like to append to the list. We also, in the book questions, there was an insert. For using the insert, the parameters would be a list, the index where you'd like to put the item, and then what item you'd like to put in the list. And a remove. And for remove, you have a list and the index of the item you'd like to remove from the list. Also, if you look at the book homework for that quiz app, they talk about how you define a list. In pseudocode, you use square brackets and then whatever items you'd like to put in your list. Separated by commas. And then if you ever want to pull an item out from the list, just one of the items, you use your square brackets to indicate which item you'd like to display. So if you want to display land, you would do list and then square brackets with a 2. And so that's how you use pseudocode with the list for programming. So that's a summary of Chapter 5. That's what you did in this chapter. Please make sure you spend some time reviewing vocabulary. Please make sure you've answered all of the Chapter 5 textbook questions, and the test is tomorrow.